Welcome back. Problem 6-27. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Material by R.C. Hibbeler. So statement is draw the shear and moment diagram for the beam. So you can see this is an overhanging beam and there is a triangular load of magnitude W0 at this end. At this end load is 0. There is a roller support at A and at point B we have pin support. So you have to draw the shear and moment diagram for the beam. So let's start with the solution. So first step is that if you remove this roller support at point A, so you will be having reaction force offered by this support on this beam will be RA, and if you remove this pin support, so there will be a vertical reaction force of RB on this beam by this support. So first we will find this RA and RB by using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point B is equal to 0 and taking the counterclockwise moment as positive. So you can see one load is RA, the second is RB, and the third one is if this triangular load is converted into a point load, so it will be equal to W1/2 into W0 into the length over which act, and this total length of the beam is equal to L. This is L because 2L by 3 plus L by 3 is equal to L, and that will act at a distance of L by 3 from point B or from denser side. So this will be L by 3. Now we apply this equation of equilibrium. So RA into perpendicular distance is 2L by 3. Let me show you. This is RA, and about point B this perpendicular distance is 2L by 3, and this is producing clockwise, so it will be negative. So I will write minus the second moment that is produced due to this load, and perpendicular distance is L by 3. Clear? And this is producing counterclockwise movement, so it will be positive. Here I have L as well because it is acting over length. So plus 1/2 this load, which is 1/2 W0 into L, W0 into L, and perpendicular distance is L by 3 is equal to 0. So from here we will get minus 2 RA L divided by 3 plus 1/6 W0 L square is equal to 0. So you will get 2 RA L by 3 is equal to 1/6 W0 L square, and when you calculate RA will be equal to W0 L over 4. So this is the value of RA. Now we'll find this RB by using equation of equilibrium, that sum of all force along y direction must be equal to 0 and upward force is taken as positive. So RA and RB are upward, so RA is W0 L by 4 minus this force, which is W1/2 W0 into L plus RB is equal to 0. So if you take LCM, so this will be 4. So it will be W0 L minus 2 W0 into L plus RB is equal to 0. So this will give you 4 minus W0 into L plus RB. So from here you will get this RB will be equal to W0 L over 4. Now you have RA and RB. So what we are going to do is that we will cut the beam at this and at this section. Let this is section AA and this is section BB, and we will find the equation of shear and moment as a function of X. Clear? And then we will put the value of X to find the shear and moment, and then draw the shear force and bending moment diagram. So first step is that if you cut this beam over here, clear, and let this distance is X, this is section 1, and draw the free body diagram. So let me draw it first. This is the beam, clear, and you will be having a triangular load Clear? This is the triangular load. This is the distance x where you cut this beam. And when you cut it, you will be having a shear force V and you will be having moment M. This is your point 1. Clear? Now you can see that here the load is W naught. So if you take the ratio, we have two similar triangular. One is this one and the other one is this one. So this is for the length of L and this is for length of X. Clear? So by using similar triangles, if I take the ratio, this W naught over length L, W naught over length L will be equal to, here let the magnitude is W. So W divided by this distance X. So W divided by X. So where we will find W will be equal to W naught into X divided by L. So here the magnitude will be W is equal to W naught into X by L. Now when you convert this triangular load into point load or concentrated load, so it will be equal to 1 over 2 this load which is W naught X over L and the length over which act, and that length is X, and that will be acting at a distance of X by 3 from this point 1. Now we'll find this V and moment by using equation of equilibrium. So first equation of equilibrium is that sum of all force along y direction must be equal to 0 and upward force is taken as positive. And remember that section AA is for x is greater or equal to 0 and less or equal to L by 3. So x start from here is equal to 0 and at here you can see x is L by 3. So this equation will be valid for this region. Clear? Now V is downward, so minus V minus this load is downward. So minus 1 over 2 W naught X square over L is equal to 0. So from here you will get V is equal to minus W naught X square over 2L. Let this is your equation number 1. Now we'll find this moment by using equation of equilibrium that sum of all moment about point 1 is equal to 0 and taking the counterclockwise moment as positive. So about point 1, the first moment is due to this load and perpendicular distance is x by 3. This is counterclockwise, so it will be positive, and there is external reaction moment which is counterclockwise, so it will be also positive, and their sum must be equal to 0. So I will write m plus 1 over 2 into W naught X square over L, which is the load, and perpendicular distance is x by 3 is equal to 0. So from here this moment will be equal to minus W naught X cube over 6L. Let this is your equation number 2. Okay. Now what we will do that this equation 1 and 2 are valid for region x is greater or equal to 0 and less or equal to L by 3. Now we will do is that we will go to and we will cut this beam at section 2 for region x is greater than L by 3 and less or equal to L, and we will draw the free body diagram. So let me draw the free body diagram over here. So let this is the beam. The total length is given as x where we have cut it. Here this is x, and there is a uniformly increasing load or triangular load. The magnitude at this point will be again that will be equal to W naught X over L. You can see you will have two similar triangles. One is this one and other one is this one. So if you take the ratio of their side, W naught over L will be equal to, here the magnitude is W, so W over X. So from here W will be equal to W naught X over L. So we will write it over here. Okay. And at point X is equal to at length L by 3. Length L by 3, we have RA, which is equal to W naught L over 4. So this remaining distance will be equal to X minus L by 3. Clear? So when you cut it, you will be having a shear force V and you will be having a moment in this direction. And this is your point 2. So we'll find this V and M by using equation of equilibrium. And this is for region X is greater than L by 3 and less or equal to L. So sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see this is a triangular load. So when converted into a point load, so it will be equal to 1 over 2 this load, which is W naught X over L into the length over which it acts, that is X. So this will be equal to minus W naught X square over 2L, and this load which is W naught L over 4, which is upward, W naught L over 4 minus V is equal to 0. So from here you will get V will be equal to minus W naught X square over 2L plus W naught L over 4. Let this is your equation number 3. Now we'll find this moment by using equation of equilibrium, that sum of all moment about point 2 is equal to 0 and taking the counterclockwise moment as positive. So about point 2 first moment is this W naught L by 4 and perpendicular distance is X minus L by 3. This is producing clockwise, so it will be negative. So I will write minus W naught L by 4 into X minus L by 3. The second moment is due to this load, which is W naught X square over 2L and perpendicular distance. It will act at a distance of X by 3 from this end, from this point 2. So total length is X, so it will be X by 3. And this is producing counterclockwise movement, so it will be positive. So I will write W naught X square over 2L into perpendicular distance is X by 3, and there is external moment which is plus M, that will be equal to 0. So you will get this moment will be equal to W naught L over 4 into X minus L by 3 minus W naught X square X cube over 6L. Clear? Let this is your equation number 4. Now you have equation 1, 2, 3, 4. So let me copy it and we will move toward next page in order to draw the shear force and bending moment diagram. Let me copy this for our ease. I'm going to copy it and we will move toward next page and we will paste it over here and we will resize it. Okay. Now we will find shear force for various length. So for X is equal to 0, put in equation number 1. This is your equation number 1. So you will get V is equal to 0. So for X is equal to L by 3 at this point A. So put in equation number equation number 1. So you will get V is equal to minus 1 W naught L over 18. You can just put it and you will get the different values. Now for X is equal to L, you can put it in equation number 3. Equation number 3. This is equation number 3 that is valid for X is greater than L by 3 and less or equal to L. So you will get V is equal to minus W naught L over 4. And at the end you can see you have RB, which was W naught L over 4, which will cause it to the 0. Okay. So let me draw the shear force diagram first. So if you take the vertical line from the end of the beams and there is a horizontal line to show the length x, on y-axis we have shear force. Okay, so at first point we have x is equal to 0, v is equal to 0. So first point will be this one, and at x is equal to, here x is L by 3. L by 3. So v is minus w naught L over 18. Let this point is minus w naught L by 18. Clear? And you can see this load is a linear load, so shear force is a second degree curve, and that is negative. So this, we will join these 2 points and we will get the shear force like this. And here at point A you can see that you have already reaction force, which was w naught L by 4. So minus w naught L by 4 plus w naught L minus w naught L over 18 plus w naught L over 14 will give us w7 w naught L over 16. So let this point is 7 w naught L by 16. So shear force will change from this point till this point. This will be the point. Okay. Again, you can see that at the end you have x is equal to L. Here x is equal to L. We have w minus w naught over 4. So let minus w naught over 4 is this point, minus w naught L over 4. And you can see that this is a linear load, and you can see from the equation number 3, this is second degree curves and the slope will be in decreasing, or you can see it will be in clockwise direction. So you will get this shear force at the end is this. Now here you will see that shear force is equal to V is equal to 0. So you will find the location of this V, because here the bending moment will be maximum. So we will find this X. Clear? So what we will do is that put V is equal to 0 in equation number 3. This is equation number 3, you can see. So V is equal to minus W naught X square over 2L plus W naught L over 4. And when you simplify it, you will get X square is equal to L square over 2. And we will get X is equal to 0.707 times L. Okay. Now we'll move toward drawing the bending moment diagram. So for that, I will draw a horizontal line from the end of the beam to show X in length, and we'll extend these sides. Okay. On y-axis, we will be having moment. So what we will do is that put X is equal to 0 in equation number 2, which is the moment equation for region X is greater than 0 or less or equal to L. So you can see this, the equation. So if you put X is equal to 0, so moment will be equal to 0. So moment will be equal to 0. So your first point will be this point. Now put X is equal to L by 3 in equation number 2. Again, let me show you, this is equation number 2. So if you put X is equal to L by 3, so it will be this one. And if you simplify it, so you will get the moment will be equal to, let me write it, the moment will be equal to 0 minus 0.00617 W naught L square. So let your, if I project this point, so this will be the L by 3 length. So here we will plot minus 0.006. So let minus 0.6 is this, well, minus 0.00617 W naught L square. And you can see this moment equation is third degree equation, and that is negative. So it will be like curve, it will be like this one. Okay. Now at x is equal to, we have shown that at x is equal to 0.707 L, this is x is 0.707 L, what will be the moment? So put it in equation number 3, equation number 4, because equation number 4 is for region x is greater than L by 3 and less than L. So you will get moment will be equal to 0.0345 W naught L square. So plot it, let at x is equal to, this is the length where we have maximum bending moment. So let maximum bending moment at this point is 0.0345 W naught L square. And you can see this is this equation is third degree, clear, and this positive value. So or you can see that shear force is in downward direction, so bending moment will be 1 degree higher, it will be third degree equation, and the slope will be, or the curve will be in clockwise direction. Okay. Now at x is equal to, at x is equal to L, so put in equation number 4. So when you put it in equation number 4, you will replace x with L, so you will get this moment will be equal to 0. You can put it and you can calculate, so you will get moment will be equal to 0 at this end. So this will be your last point, and again you can see it will be, as this shear force is a second degree curve, so bending moment will be third degree curve, and it will be like this. So we'll join this like a curve and it will give you like this. There, so here shear force will be 0 and here length will be equal to L. Clear? And that is your bending moment diagram, BMD, and this is your shear force diagram. And that was all about this problem 6-27. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.